So welcome. As Matt said, my name is Gijs van der Hoorn. I work at the Delft University of Technology at the Department of Cognitive Robotics. And my co-presenter is Murat Belsh, who works at MathWorks. And I'm going to be presenting some work we did to enable automated code generation of Simulink models as ROS control controllers, as you can see on the slide. And I'm going to try and actually go to the next slide now. Otherwise, Murat will have to do this for me. Murat, could you do this for me? It doesn't seem to be working.
All right.
Okay, so we'll just do it this way then. Now, to give a little bit of introduction, what we are going to be talking about is actually using Simulink's code generation to create ROS control controllers. And the reason we want to do this is because Simulink obviously makes some quite nice things possible, especially on the side of model-based design. If you're not familiar with Simulink, it's a MathWorks product in which you can develop a plant, a controller in a graphical way, similar to what we saw earlier in the presentation by Christoph, but then specifically for control systems. And then you can also simulate the plant and finally simulate the controller together with it using model-driven or model-in-the-loop simulation, for instance. And at the end, you can actually use code generation to take whatever you designed in Simulink and generate it out into various programming languages such as C, C++, but also HDL, for instance, and many others. And the main reason you want to do this is because it just reduces hand coding a lot and reduces your time to market. So our motivation comes down to why not take that infrastructure from Simulink for design and testing of controllers and try to integrate that a little bit better with what we have in ROS. And in ROS, we have something called ROS control, which actually allows us to run controllers in a hard real-time execution context on the one side, and on the other side with ROS standard ROS interfaces. And what we get by doing this is obviously we get to use Simulink, so we get to use model-based design principles for the design of the controllers. We are able to actually test it in simulation and actually validate that the controllers work in that simulation. And in the end, we press a button, ideally, and we end up with well, the code that represents the same graphical model, but then in a ROS control package. And somewhere in mid-2020, I took this idea, which was really just an idea at that point, and I talked to Matt and then finally to MathWorks, and luckily they saw the benefit in this as well, and we partnered up to try and get Simulink and ROS control to do nice things together. So that's the motivation behind the project. And today I'm going to be giving a very brief overview of what we ended up doing and what the current status is. And first I'm going to give you a short ROS control overview. So what is ROS control? For those of you not familiar with it, it's essentially a generic set of tools for the control of robots. And at this point, it's mostly PID, which are part of the standard controllers which come with ROS control. It's a generalization of what was called back then the Peer-2 mechanism controllers package, and which was used to control the Peer-2, which was already hard real-time capable and had many of the parts that ROS control has these days. But now there's nothing Peer-2 specific anymore in it, so it's usable for all sorts of robots. It's extensively used in both ROS-I, and there is now also a ROS-II version. And I think we'll be hearing a bit more about the ROS-II version of ROS-II control or ROS control or when we hear something about the Universal Robots driver for ROS-II. And it's used by both enthusiasts and OEMs. And there are some quite well-known names there in the list. UR's there, as I mentioned earlier. The ABB recently released a ROS control-based driver as well. And ClearPath had lots of robots with ROS control compatible drivers. It consists of two main parts. At a high level, there is on the one side the abstracted hardware interface. this includes simulators, so both simulators and real hardware are supported. And on the other side, there's a set of controllers which use the hardware interfaces to expose standard ROS interfaces to the rest of your application. And an example of such an interface would be the follow joint trajectory interface, which people typically use for with MoveIt, for instance, in Tesseract. And some of the aspects that are or characteristics which are quite interesting is that the ROS control architecture has decoupled the execution policy. So the control flow, whatever decides the control flow, when things are run or how they are run, from the implementation. So it's left up to or left to an external entity, which means that, for instance, you would be able to drive it from a process which is running in a hard real-time execution context. And this means that with proper care, you can make a ROS control application completely hard real-time compatible, essentially, or hard real-time safe. It also means that, for instance, you could use an external system to drive the control flow, such as a sampling loop. And finally, the main goal of ROS control is to reuse control code. Everything else in ROS is also obviously geared towards reuse of code. And ROS control just makes this possible in a context which is more geared towards the control of pieces of hardware, essentially. Murat, could we go to the next slide, please? Yes. Okay. So as I said, there's two parts of ROS control. On the one side, there's abstracted hardware. On the other side, there's the controllers. I'm going to talk a little bit about the abstract hardware interfaces. And as I said, nothing actually talks directly to the hardware. What you do in ROS control is you implement something called a robot hardware class. And when people talk about a ROS control hardware interface, this is typically what they mean. And the robot hardware class is responsible for the robot hardware class is responsible for essentially wrapping access to all bits of the hardware. So whether it be through registers or some SDK that the OEM has provided, or through a field bus, or any of those things that you see in that list, even ROS topics, services, or actions, although that's not often done because you lose your determinism. But the job of the hardware interface is essentially to abstract that access, and that's the only part of your stack that actually talks to the hardware directly. And its main job is actually to provide the rest of the system with resources. So that would be what you see on the right side in the diagram. There's three examples of resources, actually. There's a velocity joint interface, a position joint interface, and a joint state interface. Out of the box, there's support for position, velocity, and effort interfaces, and IMU sensors and force torque sensors. But the whole system is plug-in based, so there's actually a lot of third-party implementations available for custom resources, or at least the resources that don't come supported out of the box. And the typical system consists of standard components, but also the custom resources that someone implements for their own particular robot application. And finally, the hardware interface is responsible for conflict detection. Oh, Murat, that's a bit quick. Could you go back to the previous slide, please? Is responsible for conflict detection because it exposes a set of hardware resources, and what we don't want is two controllers to try to talk to the same piece of hardware at the same time. So hardware interfaces typically have the responsibility to detect such conflicts, and then making sure that they are well, either denied or resolved. Could you go to the next slide, please, Murat? So as I said, controllers, that's the other side of ROS control, and they claim resources, not hardware, because nothing talks to the hardware directly except the hardware interface. So the controllers claim resources, and controllers expose ROS interfaces to the rest of the application. So for instance, MoveIt and Tesseract actually talk to controllers using those interfaces. And all controllers implement a state machine or a runtime lifecycle, which is actually pretty similar to the ROS2 node lifecycle, if you're familiar with that one. And so they can be loaded initialized, started, stopped, restarted at runtime. And typically they also expose dynamically reconfigurable parameters, so you can change their settings while they're running. And you could actually switch between controllers during the runtime of the application. So you could go from a position control mode to a velocity control mode. Again, out of the box, position, velocity, and effort controllers are supported for both individual joints and for groups of joints, and there's support for execution of trajectories. And I think if you're familiar with ROS control, you've probably used the joint trajectory execution controller, which is one of the most often used controllers in ROS control. This is also all plugin based, so there are controllers that go far beyond regular PID control, and I've listed some of those in the list there. Could you go to the next slide? Yes, thank you. Finally, we'll take a quick look at what a typical ROS control architecture looks like. First of all, it's a layered architecture. So we go from the bottom where the hardware is, or a simulation, as I said earlier, all the way up to the controllers at the top layer. It's all running in a single process. Multi-threading is used to combine real-time and non-real-time execution contexts. But we have to remember ROS control, or realize ROS control does not actually change anything fundamental within ROS itself. So we can only guarantee determinism within a single node. And so as soon as you start using regular ROS topics or services again or actions, then we can't guarantee anything anymore. Obviously, ROS2 is different here. Obviously, ROS2 is different here because it does actually allow real-time communication between nodes, but I'm not sure how far ROS2 control is with this. So what we see more and more is actually that OEMs are providing their own hardware interfaces, and in that sort of setup, they are responsible for all the layers up to the interfaces layer, as you can see in the diagram at the right. So everything basically except the top layer where the controllers are placed. And this obviously allows them to completely control the quality of that interface. And by doing that, so the quality in the sense, the stability of the connection, the control modes exposed, that sort of thing. And that obviously means that they are also in complete control of the customer experience when people use ROS with their products. And it's under their control, but it still allows sufficient flexibility to their users. Okay, so, oh, sorry, 2 seconds. The hardware interface is mostly responsible for data conversion. So arrows up is from hardware representation to ROS, arrows down from ROS to hardware representations. And so you see an example there going from encoded ticks to radians, and from radians to encoded ticks. It's also possible to combine different hardware interfaces from different manufacturers, and then you see all the hardware resources at the same time in your controllers, instead of having to manage all of that yourself. And obviously controllers are user facing. So having said all of that, the interesting bits are obviously in the controllers, because the hardware interface only knows how to talk to the hardware, but it doesn't know what to say. Controllers know what to say, but don't know how to talk to the hardware. So the magic is in the controllers. And doing that all manually or writing them manually is not what you want to do. So that's what we're going to be using Simulink for. Murat also already changed the top layer for a Simulink model, and the architecture then stays the same. But instead of controllers coming from ROS control, or you're writing them yourself, we'll be using Simulink to generate the code for us. And with that, I'll hand over control over this presentation to Murat, who will be telling us a little bit more about how we exactly achieved that integration. Murat?
Yep. Hello, everybody. This is Murat Belch. So I'm going to be concentrating on Simulink part of the equation. So I want to briefly go over the automated code generation from Simulink. So I believe everybody or most people are familiar with the MathWorks products, MATLAB, Simulink, and Stateflow. The idea is basically the MathWorks products give you a tightly integrated model-based design environment where you could basically design your system in a graphical language. And then once you're satisfied that everything works, you can basically simulate your plant model, controller in the simulation environment, and you click a button, out comes the C++ code. And the code generator is flexible enough so that you can integrate your C++ code in a number of development frameworks, including ROS. So again, this is a little bit of details to the previous slides. The basic idea is that user designs everything in a high level and domain-specific language, and then he could basically test this in this simulated environment where he can simulate, he can connect to planes and whatnot, and then a code generator takes that high-level language and then converts it to a general-purpose language. And then we have different sets of code generators where we basically generate C, C++ code, HTML, or GPU code. There are several success stories. For example, the NASA uses Simulink and C++ to generate embedded C++ code for their Orion program. Also, Voyage is one of the first companies to develop a level 3 automated vehicle, and they use Simulink and embedded coder to develop their entire system. So let's come to the integration of ROS control with Simulink. So we already at the MathWorks, we have tight integration with the ROS tools. You can, for example, import ROS-back files into MATLAB, and then you could work with the already recorded data, or you could basically connect to a live network on both ROS and ROS2, and then you could interact with a MATLAB script or a Simulink model to do prototyping. And then you could also actually write a ROS node in either a MATLAB script and Simulink, and then you click one button and it's deployed as a ROS node. Obviously, the advantage of this is that you have the model-based design. Also, it's a lot easier to write a ROS node in Simulink or MATLAB than writing C++ code. Now we want to add a third capability to the MathWorks ROS integration in the form of creating a ROS controller. So as a proof of concept, I'm going to briefly go through the steps of what you can do today, basically. So you don't need any extra tools here. This is an example of differential derived proportional controller to illustrate it's purposely simple to illustrate the concept. The controller that he takes in basically tries to steer the robot to a point in a 2D Cartesian coordinates. And then you can see on the right, on the left, you have basically inputs. You have a desired position, which is a set point of the controller. This is a 2D vector of Cartesian coordinates. And then you have the current position of the robot. And then we have some controller update. And then on the right part, you have the outputs, which is the left and right wheel speeds. So the hardware interface provider, in this case, is just provide the interface to the wheel speed. So we're going to basically operate, our controller is going to output wheel speeds to steer the robot to the prescribed direction. Of course, again, the advantage of developing in Simulink is the model-based design. So you can graphically model your entire system. In this case, for example, you can basically create a test bench around your system. You could, we also have integration with Gazebo, so you could simulate your robot, and then you can see whether your controller works or not. You might have test vectors and whatnot, but from like a bird's eye view, you can clearly see what your system is doing. Once you're satisfied that your controller works, and there's generating a ROS control is a 4-step affair. You create an interface model, adjust model settings, generate code, and you do a little bit of handwritten code to integrate Simulink generated code into a ROS controller. The interface model takes in, basically the controller is in the middle, as you can see, to interface to an output development paradigm. So you have to introduce a couple of blocks here. What we call is that root IO ports is the inputs and outputs of your controller. When you generate code out of this, the model class that's generated out of this Simulink model will have hoops for inputs and outputs for those IO ports. We also have a subscribe block, as you can see. So our controller is going to basically receive the set point using the subscribe block. Then you basically adjust model settings. One thing that you have to set is that you have different kinds of hardware targets, and you need to select the robot operating system, set the code generation build process to generate in code only, and then code interface to a C++ class. So again, these are basically customization features operated, supplied by the embedded coder, but then you can see that there's a lot of flexibility in terms of how you can generate code. Once the generating code is after doing this is just basically single button click, and then out comes the C++ class. So on the left, I greatly simplified the code generated out of the Simulink class. It basically has methods for initializing the Simulink model, stepping through it. Step means is one controller update, where you also have the terminate and then the methods to access the outputs of the controller. On the right is a typical ROS control class. So you have to implement some well-known methods, for example, init, update, starting, and stop as part of your ROS controller. In this model, we just instantiate Simulink model, the code generated out of Simulink model as a member variable of this ROS control controller. And then we integrate the methods generated by the Simulink into the ROS control class. For example, init calls the initialize method of the Simulink model class. Update calls the step method, which is basically a controller update, and also takes out the outputs from the Simulink class. And then when you destruct the controller class, you also call the terminate as part of that. So here's a small demo. So we basically executed this on a P3DX gazebo demo model here. On the right, you'll see that we instantiated my test controller in the RQT controller manager. This is the controller that we basically created out of the proportional controller. And on the left, I basically, from within MATLAB, I am just basically setting the desired point. I basically first set 3, 4 in the XY coordinates and then returning to 0, 0 coordinates here. As you can see, is the integration between MATLAB, Gazebo, RQT controller. You could see basically you can do all of these in one single environment. So this was proof of concept work. We purposely kept it simple by providing a derived controller, but we are still doing some work with Haj to extend this to more complicated scenarios for manipulators, for example, doing torque control. And then we are aiming for 100% automated ROS control controller. The steps here that's outlined here has basically a little bit of hand coding. We want to completely eliminate that, create blocks to specify the interfaces to hardware, and also one-click automation. So you click on one button from Simulink and out comes a ROS control class where you can compile and integrate into your ROS control controller. So the key takeaway is basically automated code generation is the key enabler for all of this to work. You develop everything in the Simulink, and then you click on one button, you generate code, and then you incorporate it into ROS control framework. And we think that the same approach will be possible for ROS2 as well. And if you have any project that involves ROS controllers with Simulink, please don't hesitate to contact us. And then here's our contact information again. Thanks, and this is it from me.